keep it in your memory to be able to answer questions in the exam. There are really not mathematical problem solving, maybe some graph problem solving, but no mathematics. That's why you have to remember. So these are some of the symbols of a varactor diode. If you zoom in closely, let me zoom in. It almost looks like a diode, but you can see at this point, there's a horizontal line. It's not a perfect triangle. Or you can have like a diode symbol, but a capacitor symbol at the bottom. You might have a regular diode symbol. On the side, you see a capacitance with an arrow. This is a variable capacitor. All three symbols may be used to show a varactor in the circuit. Another name is voltage variable capacitance, VVC, because the capacitance of this diode actually changes with the applied reverse voltage, or sometimes known as a tuning diode. You know, in a tuning circuit, you have inductor and capacitor. So this capacitor, sometimes they call it tuning diode. It acts like a capacitor which changes the value of the capacitance according to applied condition. How? When this element, this diode, is reverse biased, there will be a capacitance which shows up at the p-n junction of the diode. Now try to remember your knowledge from the first lesson, the diode, which is a p-n junction, your regular diode. For example, you can take a silicon diode, you take a p-type material and join with an n-type, you have a p-n junction. What happens in the middle at the junction when you reverse bias a diode? What happens to the depletion layer? What is the size of the depletion region for a reverse bias diode?
It expands.
It expands. Normally, no bias, there's a little bit of depletion region. Forward bias, small depletion region. Reverse bias, large depletion region. So large depletion region, the width, it is wider, the width is large. Think of the construction of a capacitor. How do you create a capacitor? Fundamentally, you have two parallel plates, right? One has plus polarity, the other one has minus polarity. Now think about the depletion region. Two ends, the left side and the right side. In the middle, there's a wide space. You know, also in the depletion region, there are carriers which do not take part in conduction. So depletion region is void of conduction carriers. There is no conduction in the depletion region. It sounds exactly like a capacitor with two plates. In the middle, you have an insulating material known as dielectric. You also know that the two different materials, they have different polarities. So when it is reverse biased, you will see a capacitance at the p-n junction of the diode. When reverse bias potential increases, what is going to happen to the depletion region? You go from -2, -4, -6, etc. volts. The more reverse bias you apply to a diode, the wider the depletion region becomes. However, when you increase the negative voltage, which means when the depletion region increases, the capacitance actually will decrease. According to this graph, apply a higher negative voltage, see what happens. The capacitance is decreasing exponentially. Because there's a formula, you don't have to remember this, but I will tell you what is the formula. CT is, this is at a temperature, Kelvin. There's a Greek letter epsilon. So let me draw the epsilon symbol. Epsilon A divided by WD. This is a formula for capacitance. Epsilon is permittivity. If you see epsilon 0, it's permittivity of free space. It's permittivity. How much electric field can be built up. A is the area of the PN junction. WD is the depletion width. So when you apply larger reverse voltage, WD is increasing. When WD is increasing, since it's in the denominator, the capacitance at that junction will decrease. There are some other formulas, but it is not necessary for solving problem. There's a voltage equation, thermal voltage equation using Boltzmann constant. So VT here, right here, VT is K times T sub K over Q. Q is the charge in Coulomb. K, small k, will be Boltzmann constant. And T sub K is the temperature in Kelvin. Here, the capacitance with the reverse bias is given by this formula, C of 0 over 1 plus VR over VT, power n. If you do not apply any reverse bias, the capacitance that you experience at the junction is given by the notation C0. N is a factor. The power n is a factor. It's for alloy material. It's the type of material with which the junction is created. For alloy, it's 1/2. Diffuse junction is 1/3. V sub T is the maximum reverse bias voltage. T here is at a temperature. When you see capital T, it's usually in Kelvin, not degrees Celsius. VR is your applied reverse bias. There is no problem to solve using this formula. I do not ask this type of problem solving, but please remember what happens in a variable capacitor diode or a varactor diode. Increasing the reverse bias will decrease the capacitance. So there are some applications in frequency modulators, FM. It is used. There are some devices which control automatic frequency by automatic way, automatic frequency control devices. Adjustable band pass filters. You have learned about filters in op-amp chapter. How do we create a filter? You can create a RC or you can create CR. One is a low pass filter, the other one is a high pass filter. I think RC is the high pass, and then if you join high pass with the low pass, you will get band pass filter. Also, you know the cutoff frequency is, it has C in the equation. So if you have a variable capacitance C in the equation, your band, the low limit and the high limit can also be adjusted using a varactor diode. If you do not want a fixed band, you want to change your band of the frequency, the band pass filter, you want to change the lower and upper frequency, you can use varactor diode. There is something called a parametric amplifier. We have power diodes. Next is power diodes. They are used in high power, high temperature application, especially power rectifier circuit, and you must have proper rating for power. You cannot take a regular PN junction diode and use in high voltage, high power applications. It will just burn out. They cannot handle the large amount of current. Sometimes instead of calling power diode, we just directly call them rectifiers. The symbol of a power diode is exactly the same as a general purpose diode. So if you are given a circuit with a diode, nothing is written, no other information is given, you cannot really say whether or not it's a regular diode or a power diode. You have to know it. You should have additional information. But if you look by physically, if you take two diodes, one is a normal size, the other one is larger size. If you compare a regular diode with a power diode, the power diode will be absolutely all the time physically larger than the general purpose diode. If you put it in a, for example, a circuit board, you create a motherboard and some circuit, they need heat sinking. The power diodes heat up really fast. So you have to put a heat sink which will take heat away from the power diode so that it does not get damaged and the components surrounding it also do not get damaged. And then it is not written here, but it's good to know that the power diode, it has much larger PN junction area compared to small signal diodes. The PN junction area, effective area, is much larger. If you have a small area, there's a limitation of how much current or charge you can pass through. If you have a larger surface area to work on, the capacity of carrying current becomes increased. For example, it is possible that a power diode in the forward bias, the forward current can be several hundred amperes. I said several hundred, 2, 3, 4, 500, that's several hundred. Not just 1 ampere, not just milliampere, but several hundred amperes can be safely handled by a proper power diode in the forward bias. What about the peak inverse voltage? Can someone guess what is the peak inverse voltage for a power diode? Or the reverse breakdown voltage, which will break it down and go to Zener region. What can be, you think, a rating for PIV for a power diode? Any idea?
Would it be relatively high compared to normal ones?
Can you give me a number, like what kind of scale?
Maybe kilovolts?
Yeah, kilovolts is 1000 volts. In the reverse bias, you can apply several thousand volts for some power diodes. For a regular diode, maybe -10, -20, -30, but for a power diode, it is possible to have several thousand. That's the difference between a regular diode and a power diode. Very high capacity. I'm just checking my camera. Okay, it's working. So again, you have to memorize so many things from this chapter. After power diode, we have tunnel diode. Some of the symbols of tunnel diodes, they have a negative resistance region. If you think about the Ohm's law, V equals IR. When you have increasing V, the current should also increase, assuming we have a fixed resistance in the diode. We have studied about DC resistance and AC resistance in chapter 2, I believe. The DC resistance and the AC, which is dynamic resistance. According to Ohm's law, when you keep increasing the voltage, you should also get increased currents with a fixed resistance. But for the case of tunnel diode, it has negative resistance region, means you increase the voltage, the current will decrease. This is happening in the forward bias region. Some of the symbols of tunnel diode, we do not have a circuit, but this is the operation of a tunnel diode. The characteristic curve that you see indicates the negative resistance region where you see a negative slope pointing or sloping towards the left. That is the negative resistance region minus R. But it is not occupying the entire of the total characteristic curve. As you can see, from 0 until certain amount of voltage, you have a very steep curve rising. Looks like linear because it starts from 0, y equals mx, although the slope is very high. And then after a certain amount of voltage, the tunnel diode will enter the negative resistance region. So the current drops off. And then after a certain amount of forward voltage again, it will start conducting like a regular diode. The black dashed line, it is not the tunnel diode line. It's the conventional PN junction. You can see at about 0.5 volt, the black dashed line starts taking off. 0.6, 0.7, you have a current conduction. It is the conventional, the regular diode. The blue curve here represents the characteristic of the tunnel diode. The region which is shaded in gray, it is your negative resistance region. The R value is minus. Typical value, the range of some tunnel diodes can be from minus 80 ohm to minus 180 ohm. You can pick a particular model and series of tunnel diodes. So for some particular series, you can have a constant negative resistance in that region. For example, negative 250 ohm. The negative R, the negative resistance region, it appears at a voltage level. At which level? Consider the two voltages. One is called here is called VP and V. When do you have the full conduction? After about 0.6 volts, you have a regular conduction, and this one around 0.1. I'm just approximating from the curve. It is not a fixed one. The negative resistance region will happen at a voltage level less than the forward biasing voltage. So here the proper forward biasing is around 0.6 volt or 0.7. The negative resistance region must be before that, not after, before that. And then once you cross that threshold, the limit where you have a conduction in the regular conduction like in a forward bias junction, then you will start getting out of the negative resistance region. If it says if the forward bias voltage is beyond the negative resistance region as we have seen it, this forward bias voltage is beyond, in this case, it will act like a general purpose diode. But if the forward bias voltage is in the negative resistance region, the diode can be used as an oscillator. Can you imagine the situation? Let's say it's like this. The forward bias, maybe we take a germanium diode, 0.3. And the negative region is still like this. So it will go like this actually. Forward bias. And then you keep repeating the wave. You will see an oscillation, like a sine wave or a cosine wave. That's why if the forward bias region is before or in, not before, in the negative resistance region, this diode you can use in oscillator circuit. You can provide an oscillation. Compared with a regular diode, a tunnel diode have much reduced depletion region. So if you compare the depletion region of a regular PN junction diode and the depletion region of a tunnel diode, we should know that the depletion region for the tunnel diode is much lower. Therefore, it is considered a high frequency device for applications where you need a switching time of nanosecond or picosecond. How do these two relate? Lower depletion region and faster switching time. Which concept did we study in chapter 2 that relates the switching time with the depletion region? Who remembers? Can anyone remember? What is the reverse recovery time of a diode? When you switch from forward bias to reverse bias, you should see from a current to no current, right? But in reality, there's a little bit of current in the reverse direction, and then it takes maybe a few milliseconds or microseconds to come back to no conduction state. That is reverse recovery time. For low frequency applications, you don't care much, but for very high frequency, if you want to go from on to off, off to on very quickly, it really matters. So tunnel diodes are good applications for high frequency cases because the reverse recovery time from conduction to no conduction, no conduction to conduction, it is nanoseconds or picoseconds. Why in the normal diode or any diode, when you switch off from forward bias to reverse bias, why does the current go in the negative region first? Because of minority carriers now, they will start flowing. In forward bias, majority carriers, they have more right to flow. In reverse bias, the minority carriers will flow. Because of the minority carrier flow, when you switch from forward to reverse, you will still see some current, and then it will become zero. There needs to be some time passed before the current becomes zero. For the case of tunnel diode, the time is nano or picosecond. That's why it is better to use the tunnel diode in high frequency applications. See, it says some of the applications are high frequency circuit, oscillator, switching network. You can generate pulse, I assume, and amplifier. Do you have any questions? Any more questions about the tunnel diode?
I don't have yet.
Okay. Move on to the next subtopic, photodiode. This one is rather interesting. The symbol of a photodiode is a regular diode, and then with the Greek symbol lambda just next to it, the voltage across, the forward bias voltage is given with the symbol V lambda, V sub lambda. The current flowing through is I sub lambda. If you see the Greek symbol lambda next to a diode or a circuit component, it has something to do with light. This is the convention. The photodiode will conduct current when light is falling, light is applied to the junction. Normally, it is operating in a reverse bias condition. So light is, what is light? It's an electromagnetic radiation. Each type of light has its own frequency and wavelength. You can have visible light, you can have infrared, ultraviolet is a light. By the definition, microwave is actually light. Radio is a light because it's electromagnetic radiation. Each one has its own frequency and wavelength. So, light of a certain wavelength, when it strikes the junction, the photodiode will conduct current. The stronger the light, means the higher the intensity of the light, the greater conduction. The intensity of the light is given by the unit foot candles. Let's see what is happening. On the y-axis, you have I sub lambda, the current in microampere. On the x-axis, you have V sub lambda. As you can see, it is in the negative region, negative voltage. So you have a light of 1,000 foot candles. You have about minus 200 microamp. You have 2,000, 3,000, 4,000 foot candles. This is the strongest one. 5,000 foot candles of light, you have almost 850 microamp current flowing in the reverse direction. Notice the lines, they have almost the same amount of separation between different levels. The distance between one line to the other, when they're parallel, they're almost parallel and same distance. It shows you a linear relationship. The more The stronger the light, the more the current. This is like a linear relationship. There is one interesting thing on this graph which is called the dark current. When there is no light applied to the photodiode, it still conducts a little amount of current. In reverse, we call it the dark current. So when you have a photodiode, you cover it completely with a black cloth, it will give you the dark current, small amount of current. It is not zero current. What do you need to do to make the current conduction zero? Say you want zero current. What do you have to do? Look at the graph, figure it out. You want zero current from the photodiode. You cannot just say, I'll put it, Ajahn, I'll put it in a dark room. No. You will still have the dark current. So what do you have to do? Where is the current zero?
At point VT.
At this point, VT, the current is zero, which means between the P and N junction means between anode and cathode, you have to apply a positive voltage VT. It depends on the model of the diode, what amount, but you have to apply a forward bias voltage VT in order for this diode to stop conducting current at all. That's the way to make it stop conducting. It's a concept question or knowledge question from the graph. Oftentimes I ask the students in the quiz and exams. I think your second quiz did not have this chapter included because we did the quiz before.
Teacher, so that the reason is we need to apply forward positive VT, right?
Forward positive VT, yes. Not negative, forward positive. Because the diode conducts in the negative voltage region.
Okay.
What can you do with the photodiode? Some practical application, you can use a security alarm. You can use this in counting packages. So I can show you actually. Let's see. I'm going to bring you to your Teams page. Just keep the screen on for a moment and I'll set up something on the Teams page. Show you an example of an application using photodiodes, or two applications rather. I think I used to put something inside the class notebook. That's why I need to relocate the file or the content. Content library. Okay, solar cell. Zener. Darlington. I don't quite see it, so that I have to draw it for you then. Let me draw it. Collaboration space. Add a page. I'll name it photodiode application. And then switch the screen. So let me draw a few things. I drew two vertical lines. You can see And then maybe I'll put a light source right here, laser light. Here I'll put a photodiode detector. Let me put this symbol. This is a detector. And Greek letter lambda. All of you can see it, right?
Yes, we can see it.
So imagine this is a door through which you have to pass. Maybe this is the vault of a bank. You have seen this kind of thing in the movie. Someone goes to rob a bank, and then there are so many invisible laser. If you put your leg or hand or body, the laser beam is broken, you have an alarm. Here's the beam. Invisible beam, you will not see, but it has intensity. So the photodiode will conduct like this. If I draw the curve, let's say for a regular amount, the photodiode is conducting. Let me put a blue line. Maybe this is the current. This is the reverse current that is being detected by a circuit. Now someone is passing, what will happen? The beam gets broken. When the beam gets broken, what is going to happen? When the beam gets broken, it means at that moment, for that moment, the diode does not receive a light. Then the current that is coming out is the dark current. You can program your circuit or device. Every time the current level goes from a regular current to a dark current, there will be an alarm sounding. So this is a security alarm. Conceptually, you can use a security alarm using a photodiode. What is the second application? You can use the occurrence of dark current. Every time the beam is broken, you register one dark current. You can use a digital counter to count how many times your beam has been broken, where it can happen possibly. Let me draw another picture. Maybe this is a conveyor belt in a sorting facility. This is a device. This is a receiving device. And then from this device, I will put a laser beam. And on the green side, you have the receiver. So the laser beam goes like this. Now, so many packages are coming. This is a package sorting facility, or it can be a factory producing canned food or a packet food. These packets are moving on the belt. The direction of movement is here. Every time a package passes through, what happens? What happens to the beam? The beam gets broken, and you register one count of dark current for a moment. So here's 1, 2, 3. You have one count, then you have two count, you have three count. You can actually write the program in your facility that how many times the beam has been broken in one direction, which means how many packets you have produced today, or how many mails you have received at the logistics facility, how many cans of food have passed through. This is another simple example. Every time you receive a dark current, the counter advances by +1. Two simple examples. Have you ever tried using photodiode in your project? Anyone doing senior project? No one?
No photodiodes involved.
Okay, no photodiodes. All right, let's go back to lecture then. Lecture slides. After photodiode, you have photoconductive cell. This is a different thing. Photodiode and photoconductive cell, they're not the same. So what is a photoconductive cell? It is a device whose resistance will change with the intensity of light. This is a positive slope or a negative slope. As you can see, this is a negative slope, linear but negative. Looks like this is a log-log graph. The y-axis is log of base 10. The x-axis also appears to be a log of base 10. Illumination means the strength of the light, how stronger it is, starting from 0.1 foot candle to 1, 10, 100,000. So yes, it's progressing in a logarithmic fashion. The stronger the light, the lower the resistance. So maybe here is 300 or 500 foot candles. You see what is the resistance? Less than 1 kilo ohm. If you have 1 foot candle of light, it is about 10 kilo ohm of resistance. What does resistance do to your current? The more resistance you have, the less current you have. The less resistance, the more current, which means the stronger the light, the more current you conduct, which should make sense. With more light, you should have more current. A photoconductive cell is actually a variable resistance which changes with applied wavelength of the light. This is the symbol. It's not a diode symbol. It's a resistor symbol, variable resistor with the Greek letter lambda written next to it. So with the intensity of light, the resistance changes. The polarity of the photoresistor cell or the photoresistor does not matter in the circuit. You know, some equipment, some device, if you have a cylindrical capacitor, there's a fixed side for plus polarity and fixed side for minus polarity. But for the photoconductive cell, just like a resistor, you can put either way, the polarity should not matter. The photoconductive cell is also called by another name. Frequently, it's called photoresistive device. The resistance is a function of light. What type of material normally is used for photoconductive cell? One of the material common is cadmium sulfide. So cadmium is Cd, and for sulfur is S. Cadmium sulfide is like this, CdS. The other one is cadmium selenide. So C and small v for cadmium. Selenium is Se. These two are the most common material for photoresistive devices. Do you know there is another interesting point? The photoconductive cell or the photoresistive device, it does not have a junction like a PN junction or a photodiode. Do not confuse the photodiode with the photoresistor. The photodiode is here. It is a diode. It has a junction. This one, resistor, does not have a junction. So what does it have? The photoresistive device, it doesn't have a PN junction. It has instead a thin layer of conducting material which is connected between the terminals. And this layer is exposed to the applied light. For example, cadmium sulfide, cadmium selenide. This is just a thin layer of conducting material, not two different types, not P or N, just a thin layer. You can also use this one as a simple voltage regulator. Let's say you have a light source applied to this one, and then you have two resistors. One will be your regular resistance, the other one will be a photoresistive device. You can use the voltage divider in order to provide the output voltage. Let's see one example, a simple voltage regulator. I'll also draw for you. I'll go back to our class notebook. I drew some sketch by myself in my notebook, so I will just try to draw it here. Can you see the screen?
Yes, we can see the screen.
So this is an input voltage, and then you have this is not an inductor. It looks like an inductor, but let's call it a light source. Light. The light is shining. And then we can put a resistor R1. Maybe we can make it a variable resistance as well. And then you can have a second resistor which will have a photoresistive cell. Put the letter lambda. And then you have V out taken across the last pair of nodes. What is the output equation? The voltage across the light is this VI, right? This is VI. VI times R of lambda divided by R1 plus R lambda. So if I write the equation using the voltage divider, it is the input voltage multiplied by the load side this will be your equation. If you decrease the VI, what is going to happen? Let's say you are applying a certain amount of voltage to the light. If you decrease the amount of input voltage, what will happen to the light?
It dims.
It dims. Means when the light is less, this photoresistive cell is receiving less light. What will happen to its resistance? Vi is going down. What will happen to the resistance? It will go up, right? And then one is going down, one is going out. Overall, your output voltage is maintained. Of course, you have an R lambda in the denominator, it will go up. So you can adjust R1 to go down. This is a voltage regulator. What happens if you try to increase the VI? VI is up now. The light will become bright. With the bright light, what will happen to the R lambda? R lambda will go down. So one is going up, the other one is go down. You can make some adjustments here with R1 in order to maintain your output voltage. This is a simple voltage regulator. It's not going to be very accurate. We are not using any IC. We are just using discrete elements. So you can use a photoresistive device for simple voltage regulation. Back to lecture slides again. IR emitters. What is IR? Infrared. Can you see infrared with your own eyes? I don't think. It is not within the visible human capacity. Human can see light from only certain wavelength. Infrared should be an invisible one. There are some diodes which emit infrared radiation. So the symbol is like this with two parallel arrows, a pair of arrows, a diode with pair of arrows. When they are forward biased, not sure if this picture should be reversed or not, they produce infrared radiation. The higher the forward current, the greater the intensity. On the x-axis you have current, forward current in milliampere, DC current. The more the current, the more the infrared radiation. It is given in radiant flux. What is flux? Is it watt? No, it's not watt. What is the unit of flux? Do you know the unit of flux? Weber, milliweber. Flux is given by BA cosine phi, I think. B is the magnetic field in Tesla. A is the area where the magnetic field works. So it is Weber. The more forward current, the more radiant flux, means the more infrared radiation. The infrared radiation can be different types of pattern. If you have a very focused beam, the beam goes like a straight line. If you have a scattered one, the beam is scattered like this. You have seen many examples of IR emitter. What is one of the everyday example of IR emitter that you use?
Remote controls.
Remote control. Right now in front of my hand, I have the air condition remote. And at the end, I can see there's a diode, which is transparent in color. Every time I press something, the battery in the circuit is providing a forward current. It emits the infrared beam, and it controls the air condition. Same for your remote, TV, anything. Sometimes you use a remote for 2 years, maybe 2-3 years. Now you press in front of the TV, nothing happens. You have to go really close, or you have to press really hard. What happens? Your battery has been depleted. It is not providing enough forward current. Therefore, the output from the infrared emitter is so weak in terms of radiant flux that the signal is not enough to do anything. That's when you have to change the battery. Also, IR emitter is a 2-terminal device. As you can see, it has only 2 terminals, like a diode. Usually, what type of diode? IR emitters, usually the most common types are solid state gallium arsenide. Gallium arsenide devices, solid state, are used to make IR emitters. So many applications: remote control, card reader, intrusion alarm. So in the alarm system that I just drew a conceptual case, the beam can come from the IR emitter as well. It doesn't have to be laser. It can be infrared beam. There is something, I don't know if people still use it. It's called paper tape reader. IR emitter is used for that. And the next subtopic is LCD, stands for liquid crystal display. Let me read the slide first, and then I'll explain a bit more. There are 2 varieties. You have seen, I think, all these 2 varieties. One of the type you have in the background is very bright, and the LED, the display itself, is black or dark. And then you might have a dark background, but the display is bright. Yes, I believe you have seen both cases. Have you? So 2 varieties, 2 types of LCDs: light background, dark display, and dark background, light display. How do you construct the LCD? There are different segments. Each segment is connected to a conductor. There are 8 in this example. There are 8 pins or conductors. Depending on how or where you put the applied voltage, different parts of the segment will light up. When you apply a voltage to a certain segment, the alphanumeric display is visible. You can have both letter in the English alphabet, or you can have a number. what amount of voltage you have to put. Depending on the type of display, depending on the model, you might need anywhere from 2 volt to 20 volts. Is LCD same as LED? No. What is LED? The light emitting diode. LCD is liquid crystal display. So my calculator is a liquid crystal display, and LED, you know, LED is used everywhere now. Even in the new cars, the rear lights, brake lights, indicator lights, they are LEDs. You can have LCD which require less power than LED. But if you compare which one is faster, LED response time is much faster than the liquid crystal display. Also, LEDs, comparatively, they have longer life. We don't expect LED lights to break down or malfunction very soon. What is the amount of power if you want to compare? Let's say you compare LCD required power with LED required power. It says LCD needs lower power. Typically will be microwatts, 10 power minus 6. For LED, the power will be milliwatts, 10 power minus 3. So LCD can be 1,000 times, it can require 1,000 times less power than the LEDs. Some additional info we need to know. For an LCD, you need a light source to work, either as an external source or internal source. There has to be a light source for LCD. Lifetime of LCD in the past, especially in the past, was a very big area of concern because they did not last long. LCD is made of liquid crystal. I'll explain what a liquid crystal is. A liquid crystal can chemically degrade. Just like your battery, when you use it for a long time, it degrades chemically. The liquid crystal is subject to chemical degradation. Another concern or consideration was turn on and turn off time. This one tells about faster response times for LEDs. Okay, what is the typical range? For the liquid crystal display, the turn on, turn off time may be between 100 millisecond to 300 millisecond. What about LED? Any guess how fast LED is? Turn on and off?
Faster than LEC?
How much? LCD is 100 to 300 millisecond. LED, how much? It can be less than 100 nanoseconds. One is milli, 10 power minus 3. LED is 10 power minus 9. A lot faster. In the past, I said LCD shelf life was a matter of concern, but now with new technology, it is possible to have more than 10,000 hours of useful life. What will be the color of LCD? It is not a fixed one. It depends on the light source in the hardware. You can have a wide variety of LCD to choose from. I have seen yellowish, like, what do you call it? Orange or light orange. It's called amber color. I've seen red, I've seen light green, blue, white. So many colors of LED. Now, I did not mention what is the liquid crystal. This is the building block of this device. So I should also mention what is a liquid crystal. It's a material that flows like a liquid, but its molecular structure has some properties which you normally would find in a solid material. So flows like a liquid, but the molecular structure is more like a solid material. You may have seen that sometimes you press hard on your calculator, there is some black thing on the screen. If you really press hard, you'll actually damage, and then the black ink will come out. That is your liquid crystal. Any questions about the LCD?
I
All
don't have.
okay, all is memorizing. You have to remember in your memory. Next one is a solar cell. Now everyone knows what a solar cell is. We have seen so many solar panels. There are two quite medium large size in our faculty. In front of our faculty building, some students did a project. And so many devices are now powered by solar cells. Nowadays, solar cells it's an area of great interest because everybody talks about alternative energy. Harnessing the power of the sunlight. It's a massive source of power. As long as the sun is alive, this energy source doesn't go away. So at the sea level, a good solar cell, it receives about 100 milliwatt per square centimeter of cell area. That is what we call the power density. The higher the power density of a solar cell, the higher the output you will get from it. 100 milliwatt per centimeter square is about 1 kilowatt per square meter. What are the common materials of creating solar cell? You can have two types of solar cells. One is called the bulk solar cell, which is large construction. And then you can have another type of construction. It is called a thin film type. For both bulk and thin film type, you can have silicon in various forms. You can use silicon for both types. Another one for bulk materials, bulk type solar cell, another common type is gallium arsenide. Why gallium arsenide for bulk type? It has high rate of absorption. It absorbs solar energy at a higher rate compared to the silicon material, and the energy conversion from the gallium arsenide type solar cell is higher. What is the relationship between light intensity and the output? The more intense, the stronger light you have on the solar cell, you'll get the more output from the cell. But it is not a straightforward case. You need to optimize the other thing. For example, how do you place the solar cell with respect to the sun? The angle of the solar cell, the placement in certain location, everything needs to be optimized. In some countries, for example, one near the equator, Singapore, 3 degrees, just 3 degrees north of the equator. The sun from the early day, midday, and late in the day, the angle is very predictable. It stays the same for the whole day, the angle. But for some countries, especially in very north, the sun angle changes. Different months of the year, the sun angle will be different. Also, the intensity of the light will be different. So if you put a solar cell in a fixed position the whole year, some months you will get good power, some months it is useless. That's why in large solar farms, the solar cells are connected with rotating motor. Depending on the position of the sun, they track it and then they move automatically to get a more steady amount of electricity. If you want to get more output voltage, you usually connect multiple solar cells in series. If you want more output voltage, you have to connect in series 1, 2, 3, 4, 5, however you need, how many you need, it's up to you. That will give you more output voltage. For the more current, you have to connect multiple solar cells in parallel. I'd like to show you an example of a house solar system from the textbook. Okay, let me finish this one and then I'll show you an example. Because this is chapter 16, the next slide is chapter 17. Thermistor. Two words are hidden in thermistor. Thermal, resistor. Thermal has to do with temperature. And then you can guess now what does a thermistor do, how it behaves. Its resistance will change according to the temperature. You see a graph? It's a negative coefficient device. When the temperature increasing, the resistance is decreasing. You can see the negative coefficient behavior from the graph. It is a line with the slope pointing towards the left. The temperature is up, the resistance is down. We call it the negative temperature coefficient. That's it for chapter 16. Nothing much. We still have 24 slides. But before I move on to chapter 17, I'll show you an example. Let me just wait here while I find out maybe it's in my computer somewhere. So the difference, what is the difference between chapter 16 and 17? Can you guess? What is the main difference? The devices that you study. In chapter 16, they are just two terminal devices, only different from the regular diode, both in construction and the characteristics. But the one you will have in chapter 17, multiple terminals, not only two terminals. That's the main difference. Just quickly go to chapter 16, find the textbook. So chapter 16 is called Other Two Terminal Devices. And chapter 17 is called PNPN and Other Devices. I'm almost there. So right here, I'll change the screen. This is from your textbook, actually. This is a nice mention with the solar cell to power the house, different types of devices in the house. What is happening? In the diagram, there are some numbers given, 1, 2, 3, 4, 5, 6. What is number 1? What is happening here? What do you see at number 1?
Industrial cell.
That is the solar panel. The solar panel gives you an output. Is this DC or AC?
I believe it's AC.
No, it's DC. The output you get from a solar panel is DC. But the devices we are using, normally we use with our main supply, they need AC. What do you do? A DC waveform is a straight line. The AC waveform is an oscillating line. So what you need to do is you need to use an inverter. An inverter, remember what an inverter does? It goes from high to low, low to high. It's like an oscillating waveform. The DC output from the solar cell goes to point number 2, and then that's an inverter. It gives you an oscillating AC output so that it is useful for your large power consuming devices. For example, your refrigerator is run on AC. It is not run on DC. Microwave is also run on AC. And then I think the new televisions, the new smart TVs, they are using DC with an adapter. But in the old days, this TV, my father's and grandfather's generation, they use it. Some of you may still have this type in your house, but we don't use it anymore. This type of TV is using AC. Number 3 is a battery. Why do we need it? Any excess amount of power that you generate, which you don't need immediately, you can store in the battery. And when it's at night, the battery will supply back, the inverter will create an AC. What is number 4? Number 4 is actually your main power line from the power company. Somehow the owner of this house has decided that, okay, I'll keep the main power line, but I'll also keep the solar. Just for the case of, just for safety's sake. Sometimes maybe one does not work, the other works. Number 5 is a hookup, a special hookup panel in your building that seamlessly combines the electric supply company's power with the power that you get from the solar, so that there is no conflict or any malfunction. This is the special electrical hookup. What is number 6? Number 6 is your devices, all the devices that you can run. In some countries, I think in some Western countries, any excess solar power that you generate with your solar panel, you can actually sell back to the grid. I don't know how successful the program was, but some countries, they do it. So the thing you get out of this one is, if you want a DC to power AC equipment, you should use an inverter.
What is number 2, Ajahn?
Number 2 is inverter. Have you seen a universal uninterruptible power supply, UPS devices? When the power goes off, immediately it gives you power back, run your fan, your TV, etc. That UPS, there's a battery inside, maybe one or more batteries. It will convert a DC waveform into an AC. This is an inverter. If you have the textbook, you can read. It is actually written everything here. Inverter is number 2, converts the DC power into the standard AC power for use in home. If you live in a very shiny country where it is sunny day almost all of the year, it is possible to use only solar power, I think, in the future. Rely only on solar power for all your needs. I don't think your air conditioner will run on solar power yet. That's a very power intensive application. Air conditioner in-house. We will switch the slide. Chapter 16 is over. In the next class, no, we still have, I should go for 10 more minutes at least. PNPN and other devices. So what are PNPN devices? First, let me show you the list. SCR, silicon control rectifier, then you have silicon control switch, SCS. We'll also study about GTO, gate turn off switch. There's an SCR which can be activated by light, we call it LASCR, Shockley diode. Here you do not get confused. In the previous chapter we studied Schottky diode or the hot carrier diode. This one is called a Shockley diode. When you pronounce it, almost sound the same, but they are not the same. Shockley is also a name of that man, William Shockley, which gave you the equation for JFET. The JFET transfer curve, we call it the Shockley curve. We also have diac and triac. There's a bit of introduction. So first, the scientists invented the 2-layer diode, the PN junction diode. And then Further research and development resulted in 3-terminal devices, 4-terminal, and even sometimes 3-layer, 4-layer, and even sometimes 5-layer devices. So in a diode, how many layers do you have? PN, 2 layers. How many layers do you have in BJT? 3 layers, PNP, or you can have NPN. We will not study 5-layer devices here, but in this chapter, we are concerned about a family of 4-layer devices. Sometimes you have 4-layer devices with a control mechanism. They are generally called by a name thyristor, Hyristor. If you have a 4-layer device with a control mechanism, there's a generic name for it called thyristor. It's mostly a term associated with silicon control rectifier, SCR. Quick introduction. It's one of the greatest interest. The silicon control rectifier is an object of one of the greatest interests within the PNPN family of devices. It was invented around 1956, almost 70 years, 64, 66, how many years now? 66 years. Common application for silicon control rectifier in relay control, time delay circuit, regulated power supply, phase control. It's a switching device for high voltage, high current operation. Just like a regular diode rectifier, the silicon control rectifier will conduct only in one direction. Recently, the more advanced SCR, they are designed to control power as high as 10 megawatt. It can handle 2000 ampere at 1800 volt. What about the frequency range of SCR? 50 kilohertz. You can use in high frequency application. One is called induction heating. There's another application which needs high frequency. It is called ultrasonic cleaning. You want to clean a surface by using high frequency sound wave. Do not touch the surface. I think this application will be used in IC manufacturing, where you cannot touch any part during the manufacturing process. There are 3 terminals for the silicon control rectifier. Let's have a look at it. You have anode, cathode, and the third one is called gate. The forward bias voltage is VF. The forward current is denoted here by IA. Here is IGT, there's a gate current. This third terminal is for control purposes only. It's a controlling element. See, the construction inside, 2 layers, PN, PN. You have anode, cathode, and gate. We can look at the next slide. How do you switch on the silicon control rectifier? First, you have to apply a forward bias voltage between anode and cathode. This forward bias is VF. And, not or, and you don't have a choice. You have to do 2 things. First, apply the forward bias. Second, apply a sufficient gate signal, which can be sufficient gate voltage and gate current. If one of the 2 things is not met, the condition is not met, the SCR will not turn on. Here we assume the silicon SCR due to its high temperature and power capabilities. The gate determines when the SCR will change from a non-conduction to conduction state, means from an open circuit to a short circuit state. But if you don't apply the forward bias, let's say you do not apply the forward bias, you just apply a basic gate signal, just the regular gate voltage and regular gate current, the SCR is not going to turn on by itself. There are cases where you can falsely turn it on. We will look at that later. Once the SCR is switched on, it remains latched on means the on state is permanently connected unless or until you do something to turn it off. So once it's on, it's on. Now you remove the gate signal. After you turn it on, you remove the gate signal, the SCR will still keep conducting. Just removing the gate signal will not turn it off. There are a few parameters here: holding current, reverse breakdown voltage, forward breakdown voltage. The holding current is the minimum amount of current you need from anode to cathode. There's a forward blocking region. In this region, the SCR does not conduct fully. And then there's a forward breakover voltage, V sub BR. Once you pass the forward breakover voltage, the forward blocking region stops and the forward conduction region happens, then you have a regular current. And in the reverse bias region, you have a small reverse current, just like the diode, and you have a reverse breakdown, PIV, peak inverse voltage, where it will break down if you apply more. So what happens about the VBR? Let me move it, the screen. VBR of F, there's a star or asterisk there. This is the forward breakover voltage. Above this, the SCR enters the conduction region. Before VBR, it is called the forward blocking region. You don't have full conduction. Sometimes in the asterisk, you have another letter. You might have VBRO. When you see VBRO, it means open circuit from gate to cathode. Sometimes you might see in the graph VBRS, S for short circuit from gate to cathode, VBRR, which means there's a resistor from gate to cathode, and then you might see VBRV, fixed bias from gate to cathode. So after F, you might have letter VBRF and then OSRV. You don't need to memorize that one. It's not written here, I just let you know. IH, the holding current at this level, it is the value of current below which the SCR switches from conduction state to forward blocking region. So if you go below, even if your V is right here, if the current goes below, you go in the forward blocking region. If you go above IH, you're gonna go back to conduction region. What are these forward and reverse blocking regions? These two regions, they correspond to the open circuit condition for the SCR. When you have an open circuit, what happens? The flow of the current is blocked. The flow of the current from anode to cathode is blocked in forward blocking region and reverse blocking region because they are like open circuit situation. And the reverse breakdown voltage exactly like your regular diode, where you exceed that region, you're gonna enter the Zener region with a lot of reverse current. In the next class, I will discuss this one more time, and then we'll talk about how to turn off the SCR. And we will talk about other devices. The topic should be finished, I think, in the next class. It's 2:52. No, let's go for 3 more minutes. Let's talk about turning it off. If you want to turn off, you don't have to do both things, either or. For turn on, you have to do 1 and 2. This one or 2. How do you do that? First, remove the power source altogether. Between anode and cathode, remove the power source. Means no bias. or you can do reverse bias the anode and cathode. Any of the two ways will turn off the SCR. Remember, the SCR cannot be switched off only by removing the gate voltage. It is not going to work, because once you turn it on, it is remain in the on state, latched on. There's another way of actually making this trick to turn off the SCR. It's called commutation circuitry. They're doing the same thing. It's like a shunt path. In the commutation circuitry, you create a parallel path for the current to flow. So if the current doesn't flow from through the SCR, it flows in the parallel path. What will happen? The SCR has no current, it will turn off. By using the commutation circuitry, the parallel path, you are just removing the power source and the current source, or you can reverse bias. Let's stop at here, slide 21. I'll take your attendance and we'll meet again next Tuesday. Mr. Balang.
Yes, sir.
Tiravut.
Yes ครับ
Napatra.
Yes.
Pakong.
Yes.
Rajay.
Yes, teacher.
Jonikan.
Yes ค่ะ
Michelle.
Yes ค่ะ
Phil.
Yes, sir.
Silicon.
Yes sir
Visalut.
Yes
Yu Cheng.
Yes, teacher.
Sesehan.
Yes, sir.
Okay, Patompong.
ยาครับ
Gongsu. Martin.
Yes, sir.
Kolawit. Pichayut. Is Pichayut here? Can you hear me? Pichayut? No, he's not here. Okay, Jingma.
Yes, I'm here.
Suanyuan.
Yes, I'm here.
Tatawat.
Teacher.
Yapeng.
Yes, teacher.
Seni.
Yes, I'm here.
Siripo.
Yes, sir.
Pitu.
Yes, sir.
San An.
Yes.
Waramet.
Yes.
Nabawan.
Yes I'm here
Natapop. Mr. Natapop.
Yes, I'm here.
Warapat. Warapat present?
Yes, sir. Hello.
Yeah. Nataya.
Yes teacher
Ichayapon.
yes sir
Komchan.
Yes, I'm
Tiradon.
Yes I'm here
Kitsanapong.
Present, teacher.
Atitya.
I'm here.
Tasin.
Yes
Sukaina.
Yes
Sirin.
Yes, teacher.
Minluinu. I have not started to look at your quiz yet. I will try to find some time during the weekend. Okay, see you on next Tuesday.
Thank you, sir.
Teacher.
Welcome.
Thank you, sir.
Welcome.